Mike Wardlaw is from the Office of Naval Research, and we've been running the Pioneer program for maybe just shy of 6 months now. But actually, long before that, this Bristlemouth project has been in the works. Office of Naval Research, along with Oceankind, I think like 2 years ago, when we were just starting to talk about this, saw this and was very interested in it. Getting something like this off the ground requires some really true believers. And I'm very excited to hear from Mike, why this sort of technology is important to you in the context of what you do with Office of Naval Research. And I'm just honored that you are here to speak with us today. So everyone, please join me in welcoming Mike Wardlaw.
Thank you. Thank you. I'll start off just explaining this cover sheet. Yesterday, I was down at UCLA and I gave a briefing on a concept that I developed about 30 years ago, started about 30 years ago, called the interceptor principle. And it got me into this headspace of trying to tease out how you make better decisions in the space of developing sensor technology or any technology. And one of the things that I discovered was the same questions coming up over and over and over again, regardless of the context. So whether it was technology or whether it was social dynamics, it seemed to not matter, which gave me kind of a pretty good clue that I was maybe on to something. But it's kind of funny that having that briefing yesterday, how well it relates to what we've been talking about today. The previous speaker and I were talking as we started today, and we immediately discovered that we were talking about the same thing. Which, every time I see that, it's a really good indicator that there's something going on here to really pay attention to. I won't go into the details of this, but what I will do is give you the connection points. The basic connection point to start with is, why should I care? That's always a really good question to ask. Why do I care about any of this? What is it about Bristlemouth? What is it about my interest that connects to this? Well, what you see here is the Ocean Battlespace Sensing Department. This is at ONR code 32. The boxes that are highlighted are things that I specifically focus on, but as you can see, there's a very large reason why I care about the ocean, about systems engineering and system design. Most of the stuff on the left-hand side is very science related, is oceanography related, and the stuff on the right tends to be more systems engineering related. It's specific systems. And that's an important distinction to make. But what's relevant is that they're all covered. All right. When I first came to ONR, one of the very first things that I needed to figure out was how I was going to manage the portfolio. What structure was I going to put in place to manage the disparate technologies, disparate requirements that I was being asked to look at. And one of the constructs that came out, I developed a development approach so that I could manage the different levels in the portfolio. The basic research, which is identified here as 6.1 research, is a specific pot of money, a program element that Congress provides. So I managed the 6.1, the 6.2, and the 6.3 portfolios, and ONR also has some 6.4 dollars. Now, what's important about that is each one of those talks to a specific delineation and the specificity of the research. The 6.1 research is typically open university type research. It is open sky. There's a science problem. There's physics that needs to be understood. All right. When you move through to 6.2, it becomes more advanced technology, and then 6.3 more towards the targeted, more specific problems that you want to address. So again, why do I care? What I discovered was, left to it on its own devices, research begets research begets research begets research. All right. And it just keeps going. All right. It never ends. All right. Which is fine. But I kind of want to do something with it. All right. The other side of it is, I want to be able to make a distinction between what I call the capacity that is developed inside of that research versus the capabilities. And I want to really tease that and make sure that those of you that are listening actually understand that there is a really distinct opportunity in pulling these things apart and distinguishing them. The capacity speaks directly to the ability to do a thing. The capability speaks to actually executing and developing that. Now, what Bristlemouth, where Bristlemouth fits is in the 6.2 layer, which is really interesting because it addresses this tech base. It is an enabling technology that allows the connection between the capacities and the capabilities. That's why it shows up for me as, oh, this is really cool, you know? And I can see how I can really integrate all of the technology base that's being developed inside that 6.2 layer and just churn out capability after capability. And you heard some of that earlier today, right? If you have this interoperable interface standard and it's available to you, and you can bring it on. What do you want to do? This sets up a base that everyone can work on top of, and it standardizes it so that the OODA loop to move things from basic capacities into capabilities becomes a lot less risky. It takes a lot less time. The OODA loop just gets tighter and shorter. So that's why I care about this. In addition, I also want to make a distinction between scientific instruments and engineered products. Again, something that is subtle, but it's really important because the objectives turn out to be very different. In science instruments, science, the whole point of science is to understand the physics of things. It's an understand, right? And inside of that, everything tends to be equally important in that space. So you want more data, more data, more data. And that's what we typically hear. And you're going to pay a huge penalty for doing that, by the way, right? But you're willing to do it in the interest of learning the science. And that's cool. That's fine. No problems. But there are some things to actually pay attention to. You know, it tends to be a problem where you need the absolute accuracy everywhere at all times. So you're swimming in data, all right? And we've all heard this. This is something to be aware of. It's not a problem in its own right, but it's something to really be aware of. As a result, it tends to be very resource intensive, right? And it's static, because when you make that determination that everything is equally important, you don't change it. It doesn't respond to the environmental conditions. It doesn't respond or change to the fact that I don't have enough energy to do this. You know, it doesn't respond to the fact that I don't have the same communication bandwidth in this area that I have in this other area of the world. So it's a static design, but you can use Bristlemouth for that. You can use Bristlemouth also, though, for engineering a system that's more responsive. The distinction between a science instrument and an engineered device is the objectives are different. For engineering the device, you're looking to leverage what you've learned and make a decision, okay? You wanna make a decision with an engineered device. What does that look like? Typically, Instead of focusing on the absolute accuracy, you're looking for things that allow you to establish stable responses and efficiencies. Okay, those are objectives that are really important in an engineered system. And what comes out of that is the thing that I really like, and that's the ability to dynamically allocate the resources that are available. All right. In my world, in the maritime world, it's a very austere environment from a resource standpoint. And so it's important that I be able to allocate those resources in a flexible and agile manner. So I've only got so much energy. If I don't have the energy, everything stops. If I don't have the space-time bandwidth product, if I don't have the bandwidth to support the information content that I am creating, stop. If I don't have the communications infrastructure to support what I'm trying to do, then I got to do something with all that data, because ultimately it needs to change form. So this whole idea of being able to have a dynamic resource allocation as part of an engineered system, again, is something that Bristlemouth actually addresses very well. So it's resource preserving in that sense. All right. I head up the maritime sensing group within Code 32. So anything and everything that has anything to do with sensing anything, I'm interested. All right. And I get bored easily, so I listen to everything. And one of the things, again, I love being able to connect the dots between things and discover what the commonalities are. One of the commonalities, I don't care what kind of sensor it is or where it is, they all have the same character. There's some data stream that you're trying to sample, and you're going to process that data stream and turn it into information ultimately. That is always the objective. That's biologically the objective for everything living. It's the objective for everything we build as a system. If it's a sensor, it's going to have that kind of construct. That's my assertion, so I'm challenging you to tell me otherwise. All right, what is sensing? Sensing always has also a transduction parameter to it. You're taking energy in some form. The mechanism used to sense that energy is transduction. It's fundamental. All right. So they all have that. They all have a framing consideration. How is the data being integrated? How is it being sampled and framed? There's always a detection process. There's often a discrimination process. Sometimes there's a tracking process. And there's always telemetry inside the system. So there's the basic things that show up. And the trick here is to recognize that in each of those individual component pieces, there are constraints. One of the constraints, again, that Bristlemouth addresses is the connectivity between those components. The more agile and the more robust those interactions can be, the more things you can plug and unplug, the more you can handle exogenous information coming in from other places to collapse the uncertainty of whatever your objective is, the better that's going to work. So the kinds of challenges that we're up against is maritime sensors are almost always clutter limited. That means that the signal of interest is buried and it's often very tightly coupled with the environment. Now, that's a very, very unique and specific comment because it has a very direct bearing on how you design the sensor and what you want to focus on. And what we tend to do is focus our attention on making quote unquote better sensors. And what we typically mean by that is more sensitive, all right? Better performing sensors in a sensitivity sense, more resolution, more precision, more accuracy, that kind of stuff. But it turns out that that doesn't address the first billet. because what you wind up unintentionally doing is sampling the noise and the clutter better. Because like I said, you're clutter limited, right? So that doesn't scale. It just doesn't scale. So don't do that. You know, a good example, these bottom things down there, I wanted to leave myself a little bit of a note. You know, hearing aids, for example, is a really great example. I mean, people have been building hearing aids for eons, right? It does not work to make them more sensitive. If you talk to people with hearing loss, they have real problems with the sensitivity of these hearing aids, right? It's not the problem. They don't need to be more sensitive. They need to be more selective. Okay, so how do you get the right problem solved? You know, one of the things that's buried in that is something I'm going to talk to. Is this? Here's the tyranny. What we tend to do is we have a set of requirements. Somebody dreams up somebody in the government, somebody in industry dreams up a set of requirements and they say, okay, this is the system that I have. Here are the requirements that I want you to go after to make my system better. All right. It's perfectly logical, but it doesn't actually speak to the problem. What it does do is it tells you what they think the problem and the solution is likely to be. It's a very, very constrained view. And it's a retrospective view because it's coming from their side looking backwards. Okay, and that's important. All right, but they're looking for me to create technology. And they're speaking in a language that isn't a technology language per se, right? So they might say, okay, I have a radar system and I need 6 more dB of performance. That's the requirement they give me. The very first question that should come out is, what is the problem? Because the problem isn't that you don't have 6 additional dB. That's the solution that you think will solve your problem. But what is the actual problem you're trying to solve? It's really, really super important to get to the essence of that problem. All right? We don't spend enough time defining those problems. All right? The resource sponsors, the people that you're going to be selling and discussing your technology with, they don't spend enough time dissecting the requirements into a series of problems. But it is absolutely necessary that those problems are very, very specifically and well defined. Otherwise, you're going to more than likely go down a soda straw on a solution. It's going to be a very, very tightly controlled solution that probably will miss, because if they get to 6 dB, it still might not work because you're in a cluttered domain. You know, what did you solve? You solved the wrong problem, and you expended a lot of resources, money, energy, time, solving the wrong problem. Don't do that. Just don't do it. What you want to do is you want to take all of the requirements that everybody's talking about. The requirements are important. You want to collect them up, compile them, and bring them up into another space called requirements. You're going to bring up to another space and you're going to dissect them and figure out what are the common problems, the universal problems that are showing up inside of that space. And if they're not going to do it, you better. Okay? And they might not do it. They probably won't do it. So you better. You need to do that. But you got to go one step farther too. The problem isn't what you're actually designing the technology for, not directly. At least this is my assertion. Okay, again, you guys are invited to push back. Convert the problems, invert the problems into a series of constraints. Okay, problems, constraints. What I mean by that is if you can define the problems in terms of a set of constraints, then your technology has a very, very simple task. Either relieve the constraint or remove the constraint. That's it. Doesn't get any more complicated. Because what you know implicitly is that if the constraint is addressed, it flows back all the way through to the requirement, right? It makes technology development straightforward. And more to the point, the communication between the problem and the technology becomes more intimate. They're speaking close, not the same language, but very close. And this separation, these connections between requirements and problems, constraints and technologies, these are not arrows. These are many-to-many connections. That's key. Because what you want to do is use what is termed an operational art perspective to address these problems. And what I mean by operational art is maximize your options while minimizing the consequences. Or in the war college sense, maximize your options while minimizing your adversaries. However you want to think about it. But the problem, the bottom line is you don't want to make decisions at the wrong time in the wrong space. You want to break the decision space up. And that's where it started with making better decisions. If you do a many-to-many connection, then what you can actually do is break the questions up and the problem up into steps that you can actually manage. And you will get better solutions and you'll get more of them. There is the interceptor principle that I talk about that was on the front page. I have a very explicit, very deterministic way of going through that process. I won't get into it here, but it's something I've developed over about 30 years to actually manage the uncertainty and the ambiguity inside of a problem like this. And the cool part is it applies to everything that I've ever encountered. It doesn't matter whether it's a technology problem or it's a political problem, a social problem. It's the same problem. And again, that's kind of cool because it universally translates across these boundaries. That's what I wanted to share. The Bristlemouth technology is, like I said, it fits in this really nice, cool niche because it actually enables all of these different capacities to show up easier and quicker as realizable capabilities that can be implemented. I mean, and if we don't do anything, that's the thing to do, right? I'm done.
Well, are there any questions that anyone has for Mike? Yes. Here, I throw it. There you go.
By the way, I want one of those.
I mean for evidence.
Clearly. That was really nicely broken down, Mike. I appreciate that a lot. I wanted to take a concept that David brought up in the last talk, which was about that quote that, you know, it's not necessarily about the technology, but it's about the society or the design within society or something like that, into that last slide that you just brought up on define the problem better. I feel like if I think about it as a lead data engineer by myself, I'm like, yeah, right, makes sense. And then I remember my team that doesn't always get that. Right. How do you like merge? How do you think about that? The two of these concepts together?
That's an amazingly prescient question because it is 100% about the team. Yeah. All right. I won't go into all the details on this, but in this country, we have a lot of diversity and we don't really exploit it for what it's really powerful at doing. And one of the things that it is really potent for and really powerful for is providing disparate perspectives on that problem. That's one of our strongest attributes, and we don't actually acknowledge it that way. It's a really powerful tool, right? So building a team is a structure that also has a process. It can have a lot of different processes, but building a team and building an effective team to go after a particular project or a particular problem requires diversity in order for it to add any significant value other than resilience. Okay, resilience is enhanced by diversity as well, but that's also a raw numbers game. That's the linear part of resilience. The non-linear part of resilience is coupled with that diversity. And that's really, really important. I mean, the reason why human beings are still on this planet is because of the diversity. We should have been knocked out of existence long before, and we may still be. Okay, but anyway, hopefully I could talk about that forever.
One last question, and then
do I need a cue or?
yeah, just long as you're ready. It's a long shot. Wow! All right.
I was curious to know, are there any projects underway within ONR taking advantage of Bristlemouth or using Bristlemouth?
I am doing my best to get my sticky little fingers on as many of the kits as I possibly can. One of the things I teach a class at the 201-3014 class up at MIT, and Tim and I have talked about, in the systems design and systems engineering, that class actually having the class, it's a capstone class, utilize the Bristlemouth as a core component inside of that capstone class. I think, I'm biased, okay, right? That the capstone classes, and I know mine, is like a perfect breeding ground for disruptive things to come out of. These kids are stupid smart. And if you throw them an impossible problem, and then you give them tools like Bristlemouth, oh my, you don't know what's going to come out of that. All right. I've had some of the most amazing conversations with people who've been working in the marine robotics area for their entire career. And they'll come into the class and they'll see what we're doing. And they'll come back and they'll say, I can guarantee you we never would have thought to do it that way. And that is freaking cool. All right. Now you put Bristlemouth in there and we can actually get it done in a semester. Okay. That we cannot do. And that really pisses me off. It really does. Because the integration of the stuff that they're doing, you can't get it done in the time of a semester. Right. So I really want to see it in the capstone classes, guys. All right. So, for example, hopefully that answers that question.
That's awesome. What a great way to end it. Thank you very much, Mike. Really appreciate it. It is awesome and just inspiring to see this going so far into so many places. And thank you very much once again for coming. We really appreciate your support. And we appreciate the support of the Office of Naval Research, as well as many of our other strategic partners. That's a hard one to say, including OceanKind, Schmidt Marine Technology Partners, Builders Vision, Dalio Philanthropies, Ocean Discovery League, Aqualink, NOAA, and So Far Ocean. I would also like to send a special thank you